Okay, so we'll get started. So I'm sorry about this distance thing, but I have no control. So anyway, so we'll get started with chapter 7, the logic circuits chapter. I hope this one is, I mean, it should be a lot, very different from what we've covered before. Um, I think you'll enjoy it a lot, more if you can enjoy electrical engineering. I don't know. So anyway, so the idea is this is more of what happens inside the computer. So whatever we've been talking about before was mainly or mainly discussed signals that are analog in nature. So they have very many different values as time moves with time, right? So as time progresses, a signal like this would take on many different values. Something like this is not how a computer functions. In a computer, a memory is either at a certain voltage level or not. You do not have various voltage levels within a memory bit, for example, that are stored inside memory, right? So, but that's where quantum computing is trying to go, right? But we're not there yet. So today, with what we are doing, you know, digital circuitry or computer circuitry in general understands, ones and zeros. One representing there is voltage, and zero there is no voltage, right? So that's what computers understand. So and that's called a digital signal. And we need to figure out in this chapter how we do whatever computers do using these digital signals, right? So using an analog signal, we looked at using op amps to multiply signals, add signals, amplify signals, attenuate signals, etc., etc. So once you bring these analog signals into a computer, how do you deal with them? Bringing them into the computer, we did not study something like that. It's called an analog to digital conversion process. We are converting from analog to digital. We will sort of get a glimpse of how something like that may happen by looking into this chapter. But then once it's into the computer, we need to figure out how to deal with it. Yeah. So the benefit of, or the nice thing about these digital signals, of course, is the fact that it's a very discrete signal, right? There's no in between. It's either lower than a threshold or higher than a threshold. Let's say you set your threshold at 0.3 volts. Anything less than 0.3 volts is 0. Anything greater than 0.3 volts is a 1, right? So versus an analog signal, if you are trying to listen to you know me here and this thing is a bit loud, right? This is background noise. Then you will be listening to me and this. You will be hearing both and you're trying to interpret what I'm saying even though this is noisy, right? But if there's a wall between us that digitizes everything that goes through, if my sound is higher than my sound is higher than this thing, then only my sound will go through, and it will be a 1. You always hear my sound. So the benefit of digital signal as well is the idea of it being more immune to noise, right? It's the analog signals. If there's an analog signal here, like this signal here, and there happens to be some noise on it due to some electrical phenomena, right? Something like that will not pass through a digital system. Digital systems will only see ones and zeros inside them. So, so sometimes we call the signals binary signals because they take on two values only, or a digital signal. So it's digital binary, sort of interchangeable. Yeah. Or your binary can also refer to the fact that it has two levels. Digital can be more general because we will have several, for example, we can represent digital signals using several number formats, but at the end of the day, the number formats will only be using binary signals. Binary meaning ones and zeros. This just repeats what I was just trying to say about the digital versus the analog signal. Anytime here, if this signal here has some noise on it, as you can see here, if you're gonna the digital representation of this noise, as long as it's greater than a threshold, it's 1, right? So versus an analog signal, there is a difference between these two domains, and you don't know which one is right, which one is wrong. If this is what you have inside your computer, then you're missing some information. But if this is what you have inside your computer as representing this digital signal, then you're not missing any information, right? Because anything beyond the threshold is a 1. And you're happy with that, and you've converted it to a 1 inside your computer, for example. Right? So So modern computing utilizes digital signal technology. So of course the objective is try to figure out, okay, how do we then the objective of this chapter is trying to figure out, okay, then how do we take a number that is equal to, I don't know, 10.5, for example, convert it to digital format, and then and represent it as a stream of ones and zeros. And then I would like to take that number and maybe perhaps perform a multiplication or perform a addition or a subtraction. So how do you do that inside a computer? So, and you can operate, so digital signals or a binary system operates in what is either called, positive logic or negative logic. Positive logic means, a high signal is considered as a 1 and a low signal considered as a 0. If I'm telling you that this another signal is represented using negative logic just refers to, the lower amplitude signal refers to a 1 and the higher amplitude signal refers to a 0. Right? Just the complementary logic here. And then, sometimes we call a logic value of 1, we call it, high, true, or on, many different names for this thing. And we typically denote logic inputs to a circuit as in capital letters as A, B, and C, etc. We will see how we use that. Okay, so if we are going to be starting with the most basic building block, our most basic building block is called a binary digit or a bit. Right? A bit is basically a space, a pocket that you can occupy with either a 1 or a 0. Right? So that's a basic building block. For example, if a logic R represents raining weather, so R equals 1 if it's raining, R equals 0 if it's not raining. So if you look at this bit that you've allocated for this rain signal, as soon as your sensor sees rain, it has a value of voltage, you will take any value of voltage greater than a certain level and convert that to a 1. Store that there, that's your bit, indicating you have rain, right? How about if you want to combine, rain, wind, sun, etc., various conditions? What you can do is maybe take 3 bits next to each other and store, rain, wind, sun, and then you store ones and zeros in these 3 bits, for example. You can do the same, of course, if you use more bits, then you can store more information. Right? So you can encode more information in more bits. So, the next sort of term that we typically use is a byte. A byte is composed of 8 bits. So 8 of these pockets we call a byte. And you've heard a lot, gigabyte, megabyte, so it's multiples of 8 bits. That's what this means. The way you look at these pockets of information, I can send, the rain, wind, sun. I can agree with you that I will every minute send 3 bits, and they will stand for rain, wind, sun. Rain, wind, sun. Right? This is an agreement between me and you. Or I can send you 3 bits together, right? And you know that, for example, the one on the right is rain, the one in the middle is wind, and on the left is sun, right? So this is called serial or parallel data transmission. Of course, parallel is much faster, right? If we already agree in advance that the first one is rain, the next one is sun, then wind, and then I send all 3 together, then I've exchanged information a lot quicker. The next time I send, it's a lot. You know which ones I'm referring to, and you will get the information out. But if I send them in a serial fashion, it's slower, right? And our computers have a combination of them. So our computers have certain signals that they exchange that are parallel, and certain signals that are exchanged that are serial. So the serial bus. The USB, for example, is a serial bus. The processor's memory interface to your RAM, for example, that may be parallel. That needs to be very fast versus, your mouse control. So what? Nobody cares about that. It can be, you're not anywhere close to how fast this computer is running. So that can be serial data, no problem. Right? So similarly, for example, the modems that, when we first had internet, of course, you have DSL, right? But when I was in college, is when we started having internet, right? So we had dial-up modems, right? So you would dial up into the internet, and it was 9,600 bytes per second or something, right? So it was all serial information. It was on 2 wires. Obviously, it was not on 8 wires or 16 wires. It was just 2 wires. It was the phone connection. It was 2 wires, serial data, serial data. So you would sit down next to the computer to download something, right? So now life is different, right? So with fiber optic connections, I mean, things are very, very different at the moment. But but today, even when you're designing an electronic board, you have to decide. I mean, you're not gonna you have a processor. A processor, for example, that is going to be looking at your process control system will have a limited number of pins around it. These pins are going to be dedicated for digital input to output. They're going to be dedicated for converting analog signals to digital signals. They're going to be dedicated to converting digital signals to analog signals. There's a limit. You have to decide, okay, there's a limited number of pins. How do I transfer? If I transfer my data all in parallel, then I need 16 of these pins to transfer, for example, 2 bytes. How about everything else I want to do? I cannot. So typically processors will have, for example, a few pins that are used for serial data transmission. And then there are many different types of serial data transmission. There's I2C, there's the USB, there's RS485, RS232, there's many types of, and all of these are different ways of agreement. So I agree with you that every 1 second I will send these 3 bytes, and I will stop for a while, and I will send you a signal exactly after 0.5 milliseconds, which means I'm done with my transmission, right? It's an agreement. So all of these are different protocols, right? So protocols just have different ways of agreeing with each other, between sender and receiver. So serial, of course, is slower than parallel, but much less wire is needed, or real estate on your circuit is required. So we first need to figure out then how to take numbers and represent them in digital form. So since we only deal with ones and zeros, then we need to figure out the logic behind taking a number and converting it to a digital format. So let's look at something we know. For example, 743.2 is the base 10 system that we all use. 1 to 10 is our typical counting system that we typically use. So how do we represent? I can represent this as 3 plus 40 plus 700, right? So and then 2 times 1/10, right? So this can be represented this way. I can 2 times 1/10 plus 3 times 10 to the 0, 4 times 10 to the 1, 7 times 10 to the 0, and I end up with my 700 plus 40 plus 3 plus 0.2. So I was able to take my number and represent it in a base 10 format using 7, 4, 3, and 2. Right? So I can do the same, but on a base 2 system. On a base 2 system, I can take my number, for example. So instead of multiplying by 10 to the minus 1, I would multiply 2 to the minus 1. And then I would take the coefficient here, and then add it to 2 to the 0, then 2 to the 1. So that's sort of the base 2 type system. So if I have a number that is 1101.1, how would I convert that? What does that equal to? So it's 1 times 2 to the 0 here. That's sort of if I start from the left of the decimal point, and then 0 times 2 to the 1, 1 times 2 to the 1, 1 times 2 to the 2 squared, and 1 times 2 cubed. That's everything I have to the left. And to the right, I have 1 times 2 to the minus 1, right? So it's similar to what I did in the base 10 type system by multiplying, a number here by the corresponding base 10 place, unit, place. So this 1101.1, for example, it would represent 13.5. If I utilize a system like this to represent numbers, and again, this is an agreement, because where is this decimal point? For example, I can move this decimal point here. Right? If this decimal point moves, then, and you only see the byte. So the corresponding data would be what? 11011, right? There's no decimal point in the computer, right? And there's no sign in the computer, right? The computer, these bits either have ones or zeros. So you have to know in advance what sort of arithmetic system you're using. You're going to say that I have one digit only to the right of the decimal point. That means that you will always take your number that you come up with and start with 2 to the minus 1, right? And then you see, okay, what sort of coefficients do I have to multiply it by to create the number that I represent stored in memory, right? So if I say, no, I have two positions or two digits beyond the decimal point. So at this point, then I will take this and multiply it by 2 to the minus 2. So 1 times 2 to the minus 2, 1 times 2 to the minus 1, and 0 times 2 to the 0, and then 1 times 2 to the 1, 2 to the 1, and then 1 times 2 squared, right? It will yield a completely different number, right? Do we agree? So it's a matter of what we agree to as a system. So there will be several number systems that we will introduce in this chapter. And the reason is it's an agreement. You agree that you will use 2's arithmetic or 1's arithmetic or binary coded decimal. They have different names. All of these will be different names for ways to represent numbers. And some of them will have advantages. So you will see some of them would be very interesting for us because it allows us to do subtraction easily. Some of them will be interesting for us because it allows us to do multiplication easily, right? So, but again, so something like this is easy for us because it allows us to represent, a number with a reasonable accuracy. Meaning, I cannot represent, 0.45 when I only have 1 point behind the decimal, right? I cannot do that, right? When I have only 1 point behind it, I'm multiplying 0 times 2 to the minus 1, or 1 times 2 to the minus 1, which is 0.5. So my increments or my resolution will be that either I have a 0.5 here or I have a 0, right? I cannot have a 0.3, for example, in this case, right? But if I have more decimal points, maybe I can add up some of these points and create something of a higher resolution, right? So it depends on, okay, what is your ultimate goal? Do you want to represent something that is, very precise, but less than 2, for example? In that case, maybe all you need to do on the left-hand side of the decimal point is what? Have something that is less, up to 2, right? How do I represent 2? 2 would be what? 2 to the 0 is 1, so I need one decimal point, one position at least. How about do I need a second position, or do I need a second bit to represent 2, a number 2? To represent 0, 1, and 2, how many bits do I need? Two is what? 2 is, remember, you only have ones and zeros, right? So it can, if you start with 2 to the 0, right? 2 to the 0 is 1. 1 times 1, I can represent 1 with 1 bit. So I can, in 1 bit, using 1 bit, I can either represent 0 or 1. So can I represent 2? I cannot. How about let's take 2 bits? 2 bits, and I take my coefficients here are going to either be 1 or 0. So I take 1 multiplied 2 to the 0, that's 1, plus 1 multiplied 2 to the 1. 2 to the 1 is a 2. So then I can represent up to 3 with 2 bits. So with 1 bit, I can represent 0 and 1 only. With 2 bits, I can represent 1 here, and then 2 here. So I can represent up to 3 with 2 bits, right? So I would need only 2 bits if I want something, a very precise decimal representation of a number, and the non-decimal portion is only up to 2. Then I only need 2 bits to represent the non-decimal part, and then I can use all of this, these 3 bits to represent my decimal portion. Then I will have the 1 times 2 to the minus 1, or then 1 multiplied 2 to the minus 2, and then 1 or 0 multiplied by 2 to the minus 3, right? So I can have three bits representing my decimal portion. I can come up, I will have a higher resolution decimal point portion representation that way, right? So who decides? It's the engineer that decides based on what he knows about his system. You typically design a system that you know. You will design a pressure sensor. You will use a pressure sensor. Your pressure sensor is known to have a certain pressure range. So I know my pressure range. This pressure range corresponds to a certain voltage that is going to be measured. Since I know the voltage that will be measured, it will fall between numbers, I don't know, minus 1 volt and 1 volt. For me to represent 1 or minus 1, I need 1 or 2 bits. And we will talk about how to represent negative numbers later, but with 2 bits. That means if I have a 1 byte to represent my data, then I can use 2 bytes, 2 bits for the 1 or negative 1 representation, and I can use 6 bits for my decimal portion. Right? So it's a decision based on your application. Right? Is everybody okay with it? We'll have a lot more examples. So to figure out what you can do with more bits, let's look at how you represent numbers in the binary system. So if I have 3 bits, the 3 bits can form 2 to the third distinct words. So I will start with all 3 being 0. This represents what? 0 times 2 to the 0. 0 times 2 to the 1 plus 0 times 2 squared. The sum of them is 0. Then this. It's 1 times 2 to the 0. The 0 is 1, so it's 1 plus 1. Plus 0 times 2 to the 1. Plus 0 times 2 squared. The sum of them is 1. Here, last one. 1 times 2 to the 0 is 1. 1 times 2 squared is 2 to the 1, sorry, is 2. So we have 3 now. And then 1 times 2 to the third, right? 2 squared, sorry. So this is 0, and then 1 and 2. Like this is 2 to the 0, 2 to the 1, and then 2 squared. Right? So 2 squared, 4. 2 to the 1 times 1 is 2. And then 2 to the 0 times 1 is 1. So the sum of them is 7. So with 3 bits, I can represent 8 unique numbers starting from 0 to 7. Okay? Of course, with 4 bits, 16, and it's from 0 to 15. So it's 1 less than the total number because you have to include 0. Okay? So we're okay with this? If I would like to take my a certain number and convert it to binary form, so a certain 10 base number, like a 343 is a 10 base number, a number that we want to convert or represent in binary form. The way we would do that is the following. I would convert decimal integers to binary form by repeatedly dividing by 2 until the quotient is 0. Then remainders in reverse order give the binary form of the number. So 343 I divided by 2 one time, I get 171. The remainder is 1. Take this 171 divided by 2, I get 85, the remainder of 1. I continue doing that, continue dividing by 2 until I get the remainder being, I get 0 with the remainder of, in this case, 1. Right? So then I go and from the bottom up to write the corresponding binary number. Now, of course, you can check your number by doing what? I can take the 1 times 2 to the 0. 1 plus 1 times 2 to the 1. Plus 1 times 2 squared. And you keep adding them up to confirm that this represents 343. Right? So you take them, so here, you start from the bottom all the way up. So 1, 0, 1, 1, and the 3 ones are these 3 ones up here. So are you okay with this? And this is for everything to the left of the decimal point. If I want to represent a fraction, so this is for convert decimal integers. This is only the integer part of the number. If I would like to convert the decimal part, instead of dividing, I multiply by 2. Right? So I will multiply by 2. I would like to represent 0.392 base 10 in binary format. So instead of dividing like before, what we do now is multiply by 2. And if I get a 1, I keep it. If I get a 0, so if I multiply 0.392 by 2, I get 0.784. So it's 0 plus 0.784. I take this 0.784 multiplied by 2, I get 1.568. So I keep the 1, and the 1 plus 0.568. So divide, always subtract 1 and keep the 1 on the left hand side to construct your binary number with using it. So you take this number, multiply it by 2. If there's a 1, keep it here, and then it's a plus the decimal portion. And you keep going. Yeah, it depends on how many digits you have to represent your bits. So for example, I was told I have 1, 2, 3, 4, 5, 6 digits to represent my decimal. Then I will do this 6 times. 1, 2, 3, 4, 5, 6 times. Right? So you do it as many times as your number of bits that you have to represent your number. Right? So now I can take whatever I did here, 343. So whatever I did on the integers and whatever I did on the decimals, and come up with a representation for 343.392. I can just put the two numbers next to each other and assume that the decimal point is in a certain location, right? And again, there's no decimal point in the computer. You will say my least significant 6 bits are going to be representing my decimal portion. My most significant, whatever number of bits, are representing my integer portion. It's just an agreement, right? Because then you will have to decide, okay, if you do decide that you want 6 bits to represent your decimal portion, then for 1 byte, you'll be left with 2 bits, right? These 2 bits, you can only represent numbers up to what? 2 to the 2 squared. So you can only represent 4 digits, 0, 1, 2, and 3, right? So if your number happens to be more than 3, then you cannot live with a 1 byte or 8-bit word anymore to represent your number or your physical phenomena, right? Then you would have to maybe use 2 bytes, right? So and that's where you can starting to consume memory, right? If you're going to represent your numbers in that way, then you have to make sure that you're going to have enough memory to represent your numbers. So this is what I was just talking about. The idea, we did it for the integers, we did it for the decimal. So we will, take this, put it here, the integers part, the representation, and the decimal representation, and this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bits. 15 bits that you've allocated to represent this number. So here I'm up to what? This is how many bits? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 can represent up to what number? 9 bits can represent up to what number? 2 to the 9. 2 to the 9 plus 2 to the 9. 2 to the 10th is 1024. This is 512. See where this, your hard disks are, either 512 megabyte, 256. That comes from this 2 to the exponent, to the certain exponent, right? So it's a certain amount of memory blocks, memory bytes that they have allocated inside the system. So this is 512 here. Right, so I can represent, if my number is 600.392, I cannot use 15 bits anymore. Right? I would not be able to use something like I would have to use a higher number of bits, or I would have to reduce my resolution on the decimal portion. Okay? I would have to stop earlier on the decimal portion. Right? And remember, the decimal here, we were multiplying by 2 and taking these numbers to represent the decimal portion. And we were stopping based on how many bits. If I stop earlier, that means I'm using less bits to represent the number, which means the resolution of that number is less. Right? So that's a compromise that you'll have to work with. Okay. Of course, we want to do math, right? We would like to be able to add, subtract, multiply, do stuff. Right? So there are some rules for binary arithmetic as well, and they're very straightforward. So these are the only rules that we have. So 0 plus 0, of course, is a 0. 0 plus 1 is a 1, no carry. 1 and a 1 is a 0 with a carry of 1. 1 and a 1 and a 1 is a 1 with a carry of 1. Okay, so that's how we perform. These are the basic rules, and we will just see how to apply them on the various numbers on some numbers. Right? So here they performed an addition of, we added these two binary numbers. So these two binary numbers, of course, we can go back and represent them in a base 10 format and figure out what they represent here, right? But for now, okay, for the binary addition, again, we just apply the top rules here. So 1 plus 1 is a 1. 1 plus 1 is a 0 with a carryover of a 1. So 1 plus 1 is a 0 with a carryover of 1. So 1 plus 1, 0, carryover 1. 1 plus 1 plus 1 is 1 with a carryover of 1. 1 plus 1 is a 0 with a carryover of 1. 1 plus 0 is a 1. All these are zeros. 0 plus 1 is 1. 1 plus 1 is a 0 with a carryover of 1. Right? So we had to add one more here for a carryover. In this way of representing numbers, right? So we will look at another way of adding numbers that are coded in a different way. So we've coded a certain decimal, integer and decimal into this format. Right? We agreed that we will code a certain decimal number into these number of bits, right? And we realized that here I have 1, 2, 3, 4, 5, 6, 7, 8 bits here. Here I have 1, 2, 3, 4, 5, 6, 7. So when I added them, I needed an extra bit. Right? So as long as we agreed and we saved that bit, it's okay. But let's say we decided that all our arithmetic will be done on 8 bits. Then if we happen to come up with something that required a carryover to represent the proper number, then we have what is called an overflow. Then you're going to get something that doesn't make sense. Right? So it will happen. And if you don't properly choose your data, so if you know that your numbers range between 0 and 1000, and you chose 9 bits. 9 bits represent 0 to 512. So you know from the beginning that you cannot represent 550. Right? Anything you try to do in that case, if you add two numbers, if you add 500 plus 500, it's more than 512. So you cannot use 9 bits to represent that. You will have some overflow. You will get meaningless information. Right? So here, fine. Here, this is theoretical without a limitation on number of bits. Here I had 7 bits originally that I was using, now I have 8. So, binary coded decimal is another way of representing numbers. So, originally we took our decimal, we took our integer number and multiplied each digit in that integer number by a certain value to come up with, we took the integer number, kept dividing by 2 to come up with a binary representation. That's one way of representing numbers, that if you agree that this is how you represent numbers, you will know how to work with it. Okay? There's another way of representing numbers. It's called binary coded decimal. And each one of these ways may have advantages in certain operations. Right? So that's why we study them generally, and then there will be advantages that we will realize in some of these formats. So binary coded decimal is people realize that there's a nice simple way to do things as well. So let's take the 93.2 base 10 number. What binary coded decimal says is that I will take each one of these digits, the 9 for example, and I will represent each of these digits using 4 bits. Right? Because 2 to the 4th is what? Right? 2 to the 4th is 16, correct? So I can represent, so a single digit is always going to be between 0 and 9. So if I represent, this 4, you take each one of these digits and digitize it using, 4 bits, and I have more than enough to represent this digit. So the binary coded decimal representation of 93.2 is you take this 9 and then you represent 9 in 4 bits. So 2 to the 1 times 2 to the 0 is 1, right? Plus, this is 2 to the 0, 1, 2, 3. 2 to the 3rd is an 8. So 8 plus 1 is 9. So I represented 9 using these 4 bits. And I represented 3 using these 4 bits. And I represented 2 using these 4 bits as well. Right? I did not do the same thing. I did not take 93 and divide by 2, divide by 2, divide by 2, and then take the corresponding outputs. And I did not take the 0.2, multiply by 2, multiply by 2 4 times to represent it. I will get a different digital representation. Right? So somebody that doesn't know what digital representation you decided to use will not be able to make sense out of what you're doing. Okay? So they have to know what digital representation is being used. So this is another example, just 197 represented in binary coded decimal. There's yet another representation. So again, I know I'm representing, I'm just showing different ways of representing numbers, right? Some of this will not make any sense to you or nothing useful. And we don't actually apply all of these techniques to figure out which one is, why all of these techniques are used, because they each have advantages in computing systems, right? But we will look at least one. So I'll introduce all of these different ones, and then we'll look at least one of them and see why it's interesting to utilize it. Okay? And we can do the same for all of the others, but again, it's not just. Yeah, of course. You will have. This is the question. I always tell you: use binary coded decimal. Use one's complement. It will have to be clear. The one's complement is when you take a number. So one's complement of a binary number is obtained by replacing the ones by zeros. So just flipping all the ones to zeros, that's called one's complement of the number. Why do we do that? I'll show you in the next slide. So because sometimes it's interesting to take the ones complement and then add 1 to it. And then when you do that, you'll end up with the negative number representation. And somebody actually sat down and came up with all of this, right? So we have a number, the ones complement is flipping all the bits, right? That's straightforward. Right? Now we have a two's complement, right? Just because we have a ones complement means that we can also have a two's complement. Right? A two's complement is a number derived by taking your binary number, then finding the ones complement. So the binary number is obtained from the process that we defined before. Let's say we have 392. We take divide by 2, divide by 2, divide by 2, divide by 2, until we get a quotient of 0. That's your binary number. Okay. So if I tell you what is the binary representation of 392, that's what you would do. Okay. Then if I tell you what is the binary coded decimal representation of 392, you take 3 encoded to 4 bits, 9 encoded to 4 bits, blah blah, encoded to 4 bits. If I tell you what is the ones complement representation of 392, you take 392, convert it to binary, and come up with the ones complement. The ones complement is taking all these bits and flipping them, inverting. So 1 becomes 0, 0 becomes 1. Right? Then I can tell you, find the 2's complement of 392. Right? So you take 392, convert it to binary. Take your binary, and then you want to figure out 2's complement. 2's complement is either you start with 1's complement, and then you add 1 to it, and then regardless of what happens at the end, you do not include your carryover. Okay, that's one way. So if you end up with a 1 plus 1, right, there will be a carryover. So you forget about carryover in that case. Or there's another way of doing it. So here, so for example, the 2's complement of a binary number is obtained by adding 1 to the 1's complement, neglecting the carry of the most significant bit, if any. Right? So you take so for example, find the 2's complement of this number. So you're given this number. We first find the 1's complement. So 1's complement is flipping all the bits. Then we add 1 to obtain this number. So I took my 1's complement here and I added 1. 1 plus 1 is 0, carry over 1. 1 plus 1 is 0, carry over 1. 1 plus 0 is 1, 0 plus 0, and then you just add these numbers. If there happens to be a carryover, right? If these were all 1s, for example, there will always be a carryover, right? So what they're saying is, don't carry over past the most significant bit. Just ignore it. That's all this means. This is one way of finding a 2's complement. The other way of finding a 2's complement is you take your number, you start from the right side, and then you keep moving to the left, and you copy each digit you see until you get to the first one. Copy the one, and then everything else flip. Right? Somebody actually came up with that. They're smart people. I don't know how they come up with that, but this is how these two are equivalent, right? This number is the same as this number. Right? So this is another way of finding the 2's complement of the number. 2's complement is what we will see why is interesting. So the 2's complement will be a way for us to represent negative values and do subtraction. So that's one of the interesting applications of 2's complement representation of a number. So for example, here, and have you programmed before, like you C programming? No? Okay. None of you have done C programming? Because when you program in C, you actually have to understand some of this stuff, because you will need to understand what is the number format that your results need to be in. Are they going to be signed? Are they going to be unsigned? Because remember, if I have 3 bits, I can represent 2 to the third. So I can represent 2 to the third numbers, 8 numbers, so 0 to 7. But also with 3 bits, I can reserve the most significant bit on the left to the sign. I can say that my numbers are only 2 bits, but if they are represented in 2 bits. So 2 to the second is 4. So I can only represent 0, 1, 2, and 3. And then I will look at the most significant bit. If it's a 0, it's a positive 3. If it's a 1, it's a negative number. Right? So I can do that. That's something you also agree to. You agree by writing code on the computer that allows the computer to understand that this is how you want to represent your number. So in C programming, that's what you would say, I want an unsigned integer, an unsigned real number. I want an unsigned, you will actually have to define that when you're programming. Okay? So that's why it's good to understand some of this stuff if you're going to program anyway. Okay, so signed 2's complement is it's basically this 2's complement format that we discussed, but where you've reserved the most significant bit on the left for the sign. The sign 2's complement is very useful in representing positive and negative. In sign 2's complement representation, the first bit is used as a sign bit. Right? So this is an interesting application now, because if I do this, if I have a sign 2's complement representation of a number, that means I have a negative number, and it happens. That means I can represent negative numbers. So if I represent negative numbers, it means I can have a positive number and add it to the negative number, because I know how to perform. The binary arithmetic will not change. The binary arithmetic will always be the same. It's the same binary arithmetic that is up here. This will always hold. So if I'm able to represent a number in a negative format, but in 1s and 0s, and then a number in positive format, in a compatible format in 1s and 0s, I will apply this binary arithmetic. This is the only thing arithmetic that I can play with. And I will be able to subtract two numbers from each other, because one of them I represented it as a negative number. Right? So that's where this is heading at. So sine 2's complement, how do you come up with that? So if the positive, so sine, okay, if the number is positive, the first bit is 0 in sine 2's complement. Where if the number is negative, the first bit is 1. Negative numbers are represented as the 2's complement of the corresponding positive number. So you will have a positive number, for example, 392. We took 392, we represented it in binary format. That's a positive number. How do you, let's say I want to subtract 392 from 392, right? So what do? I take my 392, which was represented, like we figure out how to represent that using binary system, and then I find the 2's complement of it. So negative numbers are represented as the 2's complement of the corresponding positive number. So I take my 392 and then I find its 2's complement, and then I add them together. And that is basically 392 minus 392. Right? So, and the 2's complement, we found it in two ways. You start by finding the 1's complement, adding 1, or too much information. Yes, or you take the number that you've come up with and start from the right and go to the left. Now, copy every number until I see a 1. If I see a 1, I copy it and then I invert everything else. Right? That's the 2's complement. Right? Let's do an example. I think it will help us wake up. Right? So an example. So this is number format. I think an example will be better than this. Okay. So here, this example will be more interesting. Okay. So I want to subtract 27 from 29. Okay? So 29 I can convert to binary format. How do I convert 29 to binary format? Remember, we took the number divided by 2, divided by 2, divided by 2, until we came up with a representation in binary format. Let's confirm that this is 29. Right? So how do we confirm this is 29? This is 2 to the 0, 2 to the 1, 2 to the 2, 2 cubed, 2 to the 4th. Right? So it's 4 plus 3 plus 2 plus 1, right? No, 2 to the 4th, sorry. So this is 2 to the 4th, 2 to the 4th, so 1 times 2 to the 4th is this one, plus 1 times 2 to the 3rd, plus 1 times 2 squared, plus 0 times plus 1 times 2 to the 0, right? That's equal to what? 16 plus 8 plus 4 plus 1, right? So that's 25. No, what? 8, 9, and then 16 plus 4 is 20, right? So 29. So we're okay with this? We agree this is the actual representation, and this is 27. Okay, just bear with me, 1 minute or so. So I'm saying I want to subtract 27 from 29. So what did we say? I represent 27 in its 2's complement. How do we represent in 2's complement? We go into we look at 27. I see a 1. I start from the right hand side. As soon as I see a 1, I put it down here, and then everything else I flip. So I flipped everything. All of these numbers I flipped here. Right? So this is the minus 27 representation in 2's complement. Then I do the binary math that I've done, that is governed by these rules that we did before, and you ignore carryover. Right? So 1 plus 1 is 0, carry over 1. 1 plus 0 is 1. 1 plus 1 again is 0, carry over 1. 1 plus 1 is 0, carry over 1. 1 plus 0 is 1 plus 1 is 0, carry over 1. 1 plus 1 is 0, carry over 1. And then you're going to keep carrying over, right? And then you don't add another bit here. You ignore the most significant bit carryover, right? So this is now representing what? 2 to the 0 plus 2 to the 1. So it's 2. So 29 minus 27 is 2. So we were able to do a subtraction by utilizing the idea of converting a number to binary, converting this number from binary to 1's complement, taking this number 1's complement, adding 1 to convert it to 2's complement, and performing the binary addition, right? So you see the value of this stuff that we introduced at the beginning, just to reach to this subtraction. We're not going to try to do multiplications and division, okay? We will just do addition and subtraction, and that's it. So we'll stop here, and next time we'll continue.